Okay, we were solving group whiteboard problem 10.3. Christine runs forward with her sled at 2 meters per second. She hops on the sled at the top of the 5 meter high, very slippery slope. What is her speed at the bottom? Alrighty. Let's draw what's happening here. What we're given. So we are given, she's running with the sled, okay. And then she jumps on the sled. Okay, so we know the initial is 2 meters per second. And the height is 5 meters. Very slippery. That's a hint for no friction. Okay, so here we go. There is Christine. Okay, Dr. McColgan's helped me solve these. Okay, so we have our sled and we're going to go down a hill. So our height is 5 meters. And so there's Christine running with her sled and then she hops on. So we're going to be kneeling, right? Holding on tight. So she's moving with a speed of the initial 2 meters per second. Then she's going to go boom down to the bottom. And her hair's going to be blown back because she's going really fast. Or maybe that's her scarf. I don't really know. But we have a V final down there that's going to be bigger. And I'm assuming that's, yeah, find the speed at the bottom. Okay, I forgot to write that down. So this is what we are given. And then we're going to find V final. Okay. So let's do our energy bar charts. Okay, so we want to think about, we have gravitational potential energy. So we have some initial value. We have initial kinetic energy. We have no work done. We have no friction. So at the end, we're going to just be worried about our gravitational potential final and our kinetic energy final. Okay, and I am going to just set my y to be 0 here. Y equals 0, and it's going up in that way. Okay, so this height is really my y initial. Okay, so we have some gravitational potential energy at the top, and we have some, let's say, kinetic energy. At the bottom, we have no potential, and so the kinetic is going to be this plus the gravitational, so it's going to be 2.5 on my notebook lines. Okay, so that's our bar charts, and that leads us to our conservation of energy equation. So we can just bring these down again. So UG initial plus our initial kinetic energy is UG final plus our kinetic energy final. And we know that's 0, so we get rid of that right away. And then we have, and when you're given the problem, you're probably like, wait, I don't have a mass, but we're going to see that that doesn't matter because it goes away. So we have mg y initial plus 1/2 m v initial squared equals 1/2 m v final squared. That's from here. And we have a mass in every term, so boom, 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 they go away, right? Or we could divide both sides by mass, however we want to say that. And we're trying to get this guy by itself. So the next thing we'll do, we'll multiply by 2. 2gy initial plus v initial squared equals v final squared. Okay, and then we'll take the square root of both sides. And we get v final is the square root of v initial squared plus 2gy initial. Now we can plug in. Y initial is 2 meters per second squared plus 2, and then g is 9.8 meters per second squared. Y initial is 5 meters. So let's bring up our IPython window. Another square root. Square root of 2 squared is 4 plus 2 times 9.8 times 5. So the final velocity is 10.09, so let's say 10.1 meters per second. Da-da-da. Okay, let's check our elements for presentation. We have a very nice sketch, if I do say so myself. With lots of action in it. And then we have given and what we need to find. We have our energy bar charts so that we're showing that we have initial potential and some kinetic. We don't have potential at the end, and we have lots of kinetic at the end. And we have set up our conservation of energy equation. We've done our algebra first to solve for what we want to, our unknown. Then we plug in and do our calculations, box our answer, check our units, and we are good to go.